the radioactivity, which is the very crucial role, which plays a crucial role in nuclear physics and the radioactive disintegration as well. So I hope you can see my PowerPoint presentations and everything goes right. So I am going to start you to discuss the topic. From the class 2 level, you have already heard of radioactivity, which is nothing but the phenomena that exhibited by the nuclei of an atom as a result of nuclear instability, right? So radioactivity is the property possessed by some elements such as uranium, which is the most common element, or isotopes such as carbon 12, of spontaneously emitting energetic particles such as electrons or alpha particles by the disintegration of their atomic nuclei, right? So radioactive decay, which we also know as the nuclear decay or radioactivity or radioactive disintegration or nuclear disintegration, all the say terms meaning the same idea of radioactive decay. I repeat, radioactive decay uh, can also be known as nuclear decay, radioactivity, radioactive disintegration, or nuclear disintegration is the process by which an unstable atomic nucleus loses energy by radiation. A material containing unstable nuclei is considered radioactive except for gamma decay or internal conversion from a nuclear excited state. The decay is a nuclear transmutation resulting in a daughter containing a different number of protons or neutrons or both. So when the number of protons changes, an atom of a different chemical element is created. Suppose A are being converted to element B by a radioactive disintegration. So when an atom A disintegrates to another atom B, the decaying nucleus A is called the parent radionuclide or parent radioisotope, and the process produces at least one daughter nuclide, that is B, right? So basically radioactivity is a phenomena that occurs naturally in a number of substances. Atoms of the substance spontaneously emit invisible but energetic, I repeat, spontaneously emit invisible but energetic radiations which can penetrate materials that are opaque to visible light. The effects of these radiations can be harmful to living cells, but when used in the right way, they have a wide range of beneficial applications, particularly in radiomedicines for the cure of cancer. Radioactivity has been present in natural materials on the earth since its formation. For example, in potassium 40, which forms part of all our bodies. However, because its radiations cannot be detected by any of the body's five senses, the phenomena was only discovered 100 years ago when radiation detectors were developed. Nowadays, we have also found ways of creating new man-made sources of radioactivity, some like iodine 131 and molybdenum 99 are incidental waste products of the nuclear power industry, which nevertheless have important medical applications, whilst other, for example fluorine 18, are specifically produced for the benefits of their medical use, right? So this is basically So this is an important question here, that how were the protons and the neutrons held together? These two are called nucleons, right? So the reason behind is the strong force, which is the one of the four forces that exists in nature, namely the gravitational force, the electromagnetic force, strong force and weak force. So what strong force plays is an attractive force that holds protons and neutrons together. The protons and the neutrons must be close together for this force to keep them together. And how this any element has become radioactive, I will come later in this course or in this lecture. So this is what. So this is the basics of the structure of an atom. We all know that all matter is made up of atoms, which are often bound together into groups to form molecules. Each atom consists of a nucleus at its center surrounded by a cloud of orbiting electrons, as illustrated in this figure. In reality, of course, an atom is extremely small, only a fraction of a nanometer in diameter, so that it can hardly be seen even by the most powerful of modern microscopes, and this structure has been deduced by experiment rather than by direct observation. The nucleus at the center of the atom is in fact 10,000 times smaller than the complete atom, and as the figure shows, was drawn to scale, the nucleus would not be visible at all. So if an atom were magnified 1000 million times, it would be about the size of a small party balloon. And on this scale, the nucleus would still only be the size of a speck of dust. Most of the atom is empty apart from the very diffuse cloud of orbiting electrons and the minute speck of nucleus at its center. Right? So as the picture suggests, the nucleus of an atom is composed of protons and neutrons, and the number of protons in the nucleus is called the atomic number and is given by the symbol capital Z. Because of the protons each have a charge of +1 unit and the neutrons have no charge, the total charge of the nucleus is +Z units. Electrostatic attraction between the positively charged nucleus and the negatively charged electrons holds exactly Z electrons in orbit around the nucleus when the atom is in its normal state. So the overall charge on the atom is then zero. Since atoms combine with one another to form molecules through the interaction of their electrons, it is the arrangement of the atomic electrons which determines the chemistry of the atom. All atoms with the same Z therefore belong to the same element because they behave the same chemically. The protons and the neutrons in the nucleus are collectively called nucleons. Despite its small size, the nucleus contains nearly all the mass of the atom because each nucleon is 1000 times heavier than an electron. Therefore, the total mass of the atom is given by the sum of the number of protons Z and the number of neutrons n that it contains. Thus, the mass number A of the atom is given by A is equals to Z plus N. The term nuclide is used to describe a particular nuclear species with a given combination of A and Z. The full description of a nuclide is given by writing the chemical symbol for its element with A as superscript and Z as subscript, right? So, as I already mentioned, that the radioactivity is the spontaneous emission of particles, right? Alpha, beta, gamma, and all. So here it comes. What about the stability of the nuclei? Let me first discuss the units of radioactivity. The SI unit of radioactivity is the becquerel, named in the honor of the scientist Henry Becquerel. So 1 BQ is defined as 1 transformation or decay or disintegration per second. An older unit of radioactivity is QV, CI, which was originally defined as the quantity or mass of radium emanation in equilibrium with 1 gram of radium. Today the QV is defined as 3.7 10 to the power 10 disintegrations per second. So that 1 QV is equals to 3.7 into 10 to the power 10 becquerel for radiological protection purposes. So as I have mentioned, the stability of nuclear stability means that the concerned nucleus does not spontaneously emit any kind of radiation. On the other hand, if the nucleus is unstable, it has the tendency of emitting some kind of radiation which makes it radioactive. An atom is stable if the forces among the particles that constitute the nucleus are balanced. An atom is unstable or radioactive if these forces are unbalanced, that is, if the nucleus has an excess of internal energy. Instability of an atom's nucleus may result from an excess of either neutrons or protons. The ratio of neutrons to protons, N by P, is a successful way in predicting nuclear stability. This ratio is close to 1 for atoms of elements with low atomic numbers of less than about 20 protons. The N by P ratio steadily increases as the atomic number increases past element 20, that is calcium, to about element 84. So brief about the discovery of radioactivity. You all know that in 1897 Becquerel incidentally discovered radioactivity in pitchblende or uranium mineral while studying sunlight induced fluorescence of various materials. So after him the unit of Becquerel was first discovered, and he has been awarded the Nobel Prize in Physics in 1903. After him, the Curie couple, you all know that the Pierre Curie and his wife Marie Curie studied the radioactive materials, particularly pitchblende, which was more radioactive than the uranium extracted from it, and they also got Nobel Prize. So as I have discussed the stability of the nucleus, so this is the nuclear notation as I have mentioned, that X Az, where A is the mass number and Z is the atomic number. So by helium 42, 1 also means that this helium is the element symbol, 4 is the mass number, and 2 is the atomic number. So this is very important. This shows the graph, as I called, the n by p or neutron is to proton ratio steadily increases as the atomic number increases. First element 20, that is for calcium, this one 20 for calcium, to about element 84 for polonium. So at close distances, a strong nuclear force exists between nucleons. This attractive force comes from the neutrons. More protons in the nucleus need more neutrons to bind the nucleus together. The graph above, there shown, is a plot of the number of neutrons versus the number of protons in various stable isotopes. The stable nuclei are in the pink band known as the belt of stability. This is the belt of stability. They have a neutron is to proton ratio between 1.1 and 1.5. As the nucleus gets bigger, the electrostatic repulsions between the protons get weaker. The nucleus strong force is about 100 times as strong as the electrostatic repulsions, but it operates over only short distances. After a certain size, the strong force is not able to hold the nucleons together. Adding extra neutrons increases the space between the protons, and this decreases their repulsions. But if there are too many neutrons, the nucleus is again out of balance and decays. If a heavy nucleus were to split into two fragments, each fragment would form a nucleus that would have approximately the same neutron to proton ratio as the heavy nucleus. So this high neutron to proton ratio places the fragments below and to the right of the stability curve, this one, the 1:1 neutron to proton ratio, right? So this is the reason behind the instability of the nucleus, or the origin of the unstable nuclei or radioactivity. So let's discuss the fundamental laws of radioactivity. The first one is the Soddy and Fajan's displacement law. The algebraic sum of the atomic number of the parent nuclei before disintegration should be equal to the algebraic sum of the atomic number of the daughter nuclei after disintegration. Also, algebraic sum of the mass number of the parent nuclei before disintegration should be equal to the algebraic sum of the mass number of the daughter nuclei after disintegration. So if a element X, A1, Z1 are being converted to Y, A2, Z2 plus B, A3, Z3 after radioactive decay, so this means that my A1 of element X is equals to A2 plus A3, and Z1 of element X is equals to Z2 plus Z3. This is very basic. The second one is bit more details, which is the law of radioactive disintegration. For an element undergoing radioactive disintegration, at any instant, the rate of radioactive disintegration is directly proportional to the number of nuclei of the radioactive element present at that instant. So, if n be the number of nuclei of the radioactive element present at any instant t, then according to the law of radioactive decay, my dn dt is proportional to minus n. Why minus? Because the rate of disintegration are always decreasing the total number of nuclei over time. So what happens if the proportionality constant are being replaced by a proportionality constant lambda, which is called the decay constant? So dn dt is equals to minus lambda n. The negative sign denotes that the number of undisintegrated nuclei decreases with time. And the third one is the law of successive transformations. In general, one radioactive parent element decays to another daughter element which is also radioactive. The process of radioactive decay does not cease with the formation of the daughter, but extends over many generations until a stable end product is reached. So, as indicated by the previous equation 1.2, my dn dt is equals to minus lambda n. Therefore, dn is equals to minus lambda n dt, or dn by n is equals to minus lambda dt. Therefore, if we integrate it out, dn over n from n0 to n, and minus lambda integration 0 to t dt, where n0 is the initial number of radioactive nuclei, and after integrating, we find log ln n over n0 is equals to minus lambda t. Therefore, n over n0 equals to exponential minus lambda t, where n is equals to n0 times e to the power minus lambda t. The equation gives the number of radioactive nuclei present at time t after the disintegration starts. So, how do the graph n over n0 versus time looks like? So, this is the ultimate graph of particle ratio versus time. Over time, the particle ratio n upon n0 decreases exponentially over time. So, this is a very important graph. So, a bit about the fundamental particles. You should know this. Uh, Nowadays, scientists know of a large number of so-called fundamental particles which form the building blocks of matter. Fortunately, it is only necessary to be aware of a few of these in order to understand the process involved in radioactivity. The electron is probably the most familiar of these particles, right? Electrons is probably the most familiar. Although we do not see individual electrons, we are well aware of their effects in everyday life. So it is the flow of many electrons downwards which constitutes the current that powers so many electrical devices on which the modern world relies. It is the movement of smaller numbers of electrons inside semiconductor materials which forms the basis of all electronic microchip devices. So it is also a beam of electrons from a heated filament inside a television tube which causes the phosphors on the front of the tube to glow and form the picture. The electron was first discovered in an apparatus very similar to a TV tube called a Crookes tube. In 1897, Sir J. J. Thomson found that the cathode rays emitted from the negative electrode of a Crookes tube were in fact particles. He identified that these were negatively charged and extremely light. Although we can now measure the mass of the electron accurately, 9 into 10 to the power minus 28 gram, we cannot determine its size. It is so small that even to the best of modern experimental measurements, It cannot be distinguished from a perfect point. The next fundamental particle to be discovered was the proton. The first evidence of this came in 1898 when Wien investigated the rays emanating from a hole in the negative electrode of a Crookes tube. In 1911, J. J. Thomson found that the lightest of these positive rays was about 1,000 times heavier than an electron and carried a positive charge. The particles were given the same proton in 1920 by Ernest Rutherford when he realized that if they were a fundamental constituent of all atoms. Although the proton is much heavier than the electron, it is still inconceivably light, that is 1.78 × 10⁻24 gram, so that even a million protons would still only weigh 1 millionth of a microgram. A proton is also incredibly small, but unlike an electron, its size is measurable and with modern experiments. The positive charge on a proton is exactly equal and opposite to the negative charge of an electron. Last, the other fundamental constituent of an atom is the neutron. By 1920, Rutherford had realized that the atom must also contain other particles similar to the proton but without any charge. But it was not until 1932 when James Chadwick discovered the neutron. The neutron has a size and mass nearly the same as the proton but has no electrical charge. In 1926, the theoretical physicist Paul Dirac had predicted the existence of particles like the electron but with a positive charge. These positrons were first detected in 1932 by Carl Anderson studying tracks of cosmic rays. Positrons have the same mass as electrons but a positive charge instead of a negative one. They are in fact antiparticles of an electron and will annihilate with an electron if allowed to come to rest near one. The only other fundamental particle which we need to mention is the neutrino. This was proposed by Wolfgang Pauli in 1930 as a theoretical possibility to explain some of the observations of radioactive decay. The name neutrino was given to the particle by Enrico Fermi in 1934. However, it was not experimentally verified until 1956 when nuclear reactors became available. The neutrino carries no charge and practically no mass, and so it is hardly surprising that it is extremely difficult to detect. So another important terminology in terms of radioactivity is the radioactive half-life. So the activity of a radioactive source reduced over a period of time which was different for each substance. The time taken for the activity to fall to half of its original value is called the half-life of the source. However, the activity does not fall as a steady rate, so it is not the case that the activity will have fallen to nothing after two half-lives. Instead, the activity falls at an ever decreasing rate so that in every half-life the activity will half. So as the figure shows a graph of how the activity of a source changes with time. If the activity starts out at a value 100, then after one half it becomes 50, two half it becomes 25, three half it becomes 12.5, and so on. So after two half-lives the activity will have fallen to one quarter of A0, that is 25, right? So it can be seen that the activity is falling more and more slowly, and in principle it will never actually reach zero. In practice, after sufficiently long time, the activity will have fallen to a negligible level. The shape of a curve like this is said to be an exponential, and so radioactivity is said to exhibit exponential decay. Mathematically, it formed that AT is equals to A0 e to the power minus 0.693 T upon T half. T half is the half-life,